Hello everyone, myself Manikandan, Assistant Professor, Department of Mathematics, Lower College of Science and Management, Karur. So now I am going to take a topic, group theory in abstract algebra. So group theory play a vital role in abstract algebra. So let us move to the classical definition of group theory. So first I take a classical definition of group. So first take a non-empty set, G together with a binary operation. Star defined by G comma star is called a group if the following axioms are satisfied. Yes, listen, a non-empty set G, that is a non-empty set G together with a binary operation star, it is defined by star. Okay, then G comma star is called a group if the following axioms are satisfied. So it has a 4 axioms, so we have to check the 4 axioms. So first one, closure axiom. For any element A comma B belongs to the set G such that the operation A star B also belongs to the set G, that is the resulting element which is also an element of the required set G. Then second axiom, that is associative axiom. For every A comma B comma C belongs to the set G such that A star B star C which is equal to A star B star C. For any or every element belongs to the set G, that is A, B, C, we have to take the any 3 elements for checking the associative axioms. Okay, such that A star B star C which is equal to A star B star C which is also an element of the set G, that is belong to the set G. This is second axiom, associative axiom. Then we have to move the third axiom, that is existence of identity. Existence of identity. Okay, there exists an unique element. So note that there exists an unique element E. There exists an unique element E belongs to the set G such that A star E is equal to E star A is equal to A. Okay, then this is also an element of G for every A belongs to the set G. Listen, existence of identity, that is a third axiom. There exists an unique element E belongs to the set G such that A star E is equal to E star A is equal to A, which is also an element of the set G. Then next fourth one is existence of inverse. Existence of inverse. For every element A belongs to the set G there exists an unique inverse. There exists an unique inverse, that is A inverse is also belongs to the set G such that A star A inverse is equal to A inverse star A, which is equal to E. The fourth axiom is existence of inverse for every element. Okay, for every element A belongs to the set G, there exists an unique inverse. So inverse and identity element are only unique elements. Okay, there exists an unique element A inverse belongs to C such that A star A inverse is equal to A inverse star A, which is equal to E. That is, the resulting element is the identity element E, which is also an element of the set G. Okay, a non-empty set G with some binary operation, that is following the 4 axiom, which is called a group. Okay. So now move with the example of group. So example for a group. So I am taking a number system, that is real numbers, the set of all real numbers with respect to the binary operation addition. So I am going to whether it is a group or not. That is the non-empty set real numbers which is satisfies the following 4 axioms or not. We have to whether to check the conditions. Okay. First one, closure axiom. So we already know that closure axiom means take any 2 elements. Okay, so I am taking a real number 2 and negative 3. 2 and negative 3. I have to work with the closure axiom, that is 2 plus negative 3, which gives the result negative 1, which is also an element of the set R. So closure axiom is satisfied. Then associative axiom. So to check with the associative, we have to choose the any 3 elements. Okay, so in real number system, so we have to choose any 3 elements. So I am taking for example 1, 2, 3. Okay, here my binary operation is addition, so only I have to use with the addition operation. First one, 1 plus 2 plus 3, which is equal to 3 plus 2 plus 1. The resulting element is 6, which is also an element of the set real number, or the second one is satisfied. Then third one is existence of identity. Existence of identity. The identity element for the binary operation addition, which is 0. Okay. So I am taking any element from real number R. For example 3. 3 plus 0 is equal to 0 plus 3, which gives the result. So I am taking the number 3. So which gives the result 3, which is also an element belongs to the set R. Then fourth one is inverse axiom, or otherwise existence of inverse. Okay. So I am taking a number 4. I am taking a number 4 from the real number, or otherwise, okay, 4 itself. So I am taking number 4. So you have to check with the inverse of the 4 with respect to the binary operation addition. So 4 plus the inverse of 4 is negative 4. The inverse of 4 is nothing but negative 4. 4 plus negative 4, which is equal to negative 4 plus 4 is equal to the resulting element is 0, which is nothing but the identity element 0. Nothing but the identity element 0. So identity element 0 for addition. Okay. Okay, so which is also an element belongs to the set R. So I take a set real number, set of all real numbers with respect to addition. So I have to check with the 4 axioms. Okay, so closure axiom is also satisfied, then associative, then identity, then inverse. So with all the 4 conditions are satisfied, so which is called a group. Therefore, the set of all real numbers with respect to addition is a group. Okay, so some other example for group, that is the set of all real numbers, non-zero real numbers with respect to multiplication. Non-zero real numbers with respect to multiplication is also a group. So here I am changing the binary operation multiplication. There is a difference between these two. That is, here it is a set of all real numbers, but here itself set of all non-zero real numbers, because so I am choosing an operation multiplication. Why? 0 has not an multiplicative inverse. Okay, so 0 has not an multiplicative inverse, or otherwise it is not a group. Okay, so R minus 0, that is set of all real numbers, non-zero real numbers with respect to multiplication is a group. Next I am going to tell about semi-group. So now we are seeing the group with 4 axioms. So now I am going to see with semi-group. Semi-group is nothing but the axioms only 2, that is closure and associative. Closure axiom and associative axiom with respect to the binary operation, which are all satisfied, is called a semi-group. Then monoid, which is nothing but semi-group and additional part of identity element. Semi-group with an identity element is called a monoid. Okay, for example, the set of all natural numbers with respect to addition is called a semi-group. For example, for a monoid, the set of all whole numbers with respect to addition is called a monoid. Next we have to see with the abelian group. Next, abelian group. The definition of abelian group is a group G, comma star, which satisfies the axiom, or otherwise it is a commutative axiom, satisfies the axioms A star B is equal to B star A is called an abelian group, or otherwise it is an commutative group. So instead of abelian group we use the commutative group. Okay. So next example for abelian group. For example, so set of all real numbers with respect to addition, then set of all non-zero real numbers with respect to multiplication, set of all complex numbers with respect to addition, then set of all non-zero complex numbers with respect to multiplication. So these are all the abelian groups, examples for the abelian groups. Then Zn, that is modulo n with respect to addition, is called a abelian group. Then one more examples, the cube root of unity 1 omega squared, then fourth root of unity 1 negative 1 I, then negative I. So these are all the examples for the commutative group, or otherwise abelian group. Okay, thank you.